Hello, let's talk about galaxies today. Some of their common types, their properties, and the scaling relation between their properties. Let's get started. A galaxy is a gravitationally bound system of stars, dust, and gas. The word galaxy itself is derived from the Greek word galaxias, which literally translates to milky, presumably a reference to our own galaxy, the Milky Way. Galaxies come in various shapes and sizes. So when people first started observing them, an obvious way to classify galaxies was through their shape or morphology, as the astronomers prefer to say. It was soon found that most galaxies are either elliptical or flat disks like dinner plates. Advent of technology led to observations in multiple wavebands, consequently leading to color images of galaxies. In these images, most galaxies appeared red or blue. Combining the two pieces of information together, astronomers came to the conclusion that red galaxies are elliptical while disk galaxies are blue. We now know that this is because the disky blue galaxies are forming stars actively, while the red ellipticals are evolving passively. Also note that among the disk galaxies, while some have clear spiral structure, others are more irregular in shape and hence called as the irregular galaxies. Besides these, we also see many other galaxies in the universe. For instance, sometimes two galaxies can interact with each other to form interesting looking systems, leading to the formation of even bigger galaxies. But let's talk about the ellipticals and spirals first. Edwin Hubble classified the morphology of galaxies using this scheme, which is popularly known as the tuning fork diagram. In this scheme, ellipticals range from E0 to E7 such that E0 are almost round, and there onwards the ellipticity of galaxies increases to E7. On the other hand, spirals range from SA to SC in order of tightness of the spiral arms. That is, the SAs have tightly wound spiral arms, while the SCs are more loosely wound. The spiral galaxies are further divided into normal or barred spiral galaxies. A bar is a rectangular structure made up of stars, found at the center of large galaxies. Bar is a temporary structure, that is, it lasts a few million years and then dissolves. It can reappear in the lifetime of a galaxy many times. Almost 2/3 of all spiral galaxies are estimated to be barred, including our own Milky Way. Given their abundance, some astronomers prefer to add the irregular galaxies in between the two arms of the fork. Also note that historically it was believed that ellipticals, being older, must have formed before the spirals and hence were placed at the handle of the fork. However, we now know that ellipticals are an evolved version or a product of merger of two galaxies, which may have any morphology. Most of the galaxies in dense regions, such as clusters of galaxies, are ellipticals. Elliptical galaxies are optically red because of old stars in them. Metallicity, the fraction of elements other than hydrogen and helium by mass, is also very high in ellipticals. This is again a consequence of the fact that ellipticals mainly contain old stars. Note that most of the higher order elements are mostly produced when massive stars evolve into supernovae, something that we'll explore in greater detail in another lecture. Some of the elliptical galaxies are also rotating very slowly, implying that these objects are capable of collapsing without flattening. Spiral galaxies are classified as barred and unbarred or grand design and flocculent. The grand design spirals exhibit almost continuous and high contrast spiral arms and are believed to be driven by stationary density waves. The flocculents, on the other hand, have patchy and low contrast spiral features which are primarily stochastic in their origin. The spiral arms in a galaxy contain young, hot blue stars and H2 regions, the sites of active star formation. This is why the spiral arms appear to become more prominent in the bluer optical bands or images taken in the ultraviolet wave bands. But what are the spiral arms? It might appear that these are material structures made up of stars and gas rotating around the center of the galaxy with the rest of the disk. However, this explanation cannot explain the spiral structure because we know that the disk of a galaxy rotates differentially, meaning the velocity of rotation varies as a function of the distance from the center of the galaxy. As a result, if all the material in the spiral arms were rotating together, the arms would wind up very tightly in a few rotation periods and vanish in a few million years. But in reality, the spiral structure of the Milky Way, as well as other spiral galaxies, is much loosely wound. A more convincing idea is that the spiral arms are a wave structure just like the quasi-stationary density waves on the surface of a lake. As a consequence, when the gas orbiting around the center encounters a high density region, the gas clouds compress and lead to formation of stars, accounting for the blue optical colors of the spiral arms. The fact that few blue stars are found too far away from the spiral arms evidently supports this idea, formerly known as the density wave theory of formation of spiral galaxies. As an analogy, one can imagine the dust and gas as cars and the high density regions of the stationary waves as a truck moving on a highway. While the traffic knot remains a slow moving feature on the highway, the individual cars continue to move in and out of it. Similarly, the spiral structure is a knot of high density region moving through the disk of the galaxy where gas continues to compress and form new stars. These stars then evolve or move away and their place is taken by new gas and stars which strike these high density regions. In other words, the spiral structure remains constant, even though the material in it continues to evolve, just like the waves on the lake, which appear stationary but are formed from different particles of water at different times. Next in line are the lenticular or S0 galaxies. These are believed to be a transitional class somewhere in between the ellipticals and spirals. They have a bulge which is as large as the disk, but their disks are not as smooth as ellipticals. Some of them may also contain dust and gas, suggesting they may be linked to spiral galaxies. Amongst the low-mass galaxies, the irregulars are most common. These are the most abundant types of galaxies in the local universe. They are mostly star-forming blue systems containing significant amounts of dust and gas. Morphologically speaking, one also finds peculiar systems in the universe. The differentiating factor between the irregular and peculiar galaxies is that the latter are often much more massive and a product of merger of two galaxies. For instance, it is believed that when a low-mass dwarf galaxy hits the center of a spiral, it creates a ring galaxy such as this. AGN, or active galactic nuclei, can be ellipticals or spiral galaxies. A subclass of AGN with extremely luminous centers are known as quasars. As the name suggests, these galaxies host an active and often very bright source at the center. Quasars were discovered in 1962 when radio surveys detected extremely blue star-like objects embedded in fuzzy halos. Due to their unknown nature, these objects were termed quasi-stellar objects or quasars. Quasars are believed to be a consequence of high-velocity gas spiraling into the central supermassive black hole of the galaxy. Let's first define an important quantity called magnitude. Magnitude is a dimensionless quantity used to quantify the flux or luminosity of an astronomical object. The Greek astronomer Hipparchus classified the stars visible in the night sky from 1 to 6 in decreasing order of brightness. Since the human eye's response to light is logarithmic, magnitudes are measured on a logarithmic scale. In the currently used system, magnitudes usually defined for a given waveband are such that a magnitude 1 star is exactly 100 times brighter than a magnitude 6 star. That is, each step of magnitude corresponds to an increment in brightness by a factor of fifth root of 100, which is approximately 2.51 as shown here. Magnitudes are used in two ways. The apparent magnitude represented as small m is the brightness of an object relative to a reference source observed in that waveband. It is therefore a measure of the intrinsic luminosity of the object. But distance can diminish the brightness of faraway objects. So, in order to take that into account, astronomers use the absolute magnitude represented by capital M, which is equal to the apparent magnitude of that object if it were placed at a distance of 10 parsecs from us. The Sun has an apparent magnitude of minus 27, and Sirius, the brightest star visible in the night sky, a magnitude of minus 1.5 in the visible band. The evening star Venus at its brightest is around a magnitude of minus 5. As shown here, note that brighter objects have lower numerical value of magnitude and vice versa. With this knowledge, let's now explore some statistical properties of galaxies. The first one is color. In astronomy, color is quantified as the difference in the magnitude of an object, galaxy or star measured in two different wavebands. By color, galaxies can be broadly classified into red and blue such that blue galaxies have lower value of color while the red ones have high value of color. The plane defined by the color of a galaxy together with its magnitude, which is synonymous to mass or luminosity, is a great tool for studying evolution of galaxies. As shown here, the morphology of galaxies also evolve from low-mass blue galaxies occupying the bottom left of the plane to ellipticals in the top right. In the color magnitude diagram of galaxy clusters, the elliptical galaxies form a red sequence. The blue spirals and irregular galaxies, on the other hand, have higher scatter in their distribution and are therefore called the blue cloud. The population of galaxies in between these two regions is often called the green valley, comprising galaxies transiting from one distribution to the other. As a one-dimensional distribution, the color for a general sample of galaxies is bimodal. The relative strength of the two peaks would depend upon the environment being probed. For instance, the red peak may be comparable to the blue one in and around clusters of galaxies, but much smaller further away from them. Roughly speaking, the broadband color of galaxies can also be used to estimate their stellar mass using luminosity. Another important relation is found between the stellar mass and metallicity of galaxies as shown here. Metallicity is the amount of elements other than hydrogen and helium in a galaxy. As expected, more evolved galaxies will have higher metallicity because the higher order elements created by evolving stars will accumulate to enrich it. On the other hand, young, low-mass galaxies have neither had enough time to accumulate metals nor do they have potential wells deep enough to sustain them. As a result, stellar outbursts such as supernovae explosions and stellar winds can throw away many metals out of low-mass galaxies. It is also noteworthy that the M-Z relation evolves as a function of redshift. We believe this is because the high redshift galaxies were metal poor relative to the present day galaxies, which have had enough time to accumulate metals created in evolved stars. Let us now look at the distribution of galaxies and try to answer, say, how luminous are the most common galaxies in the local universe. To do so, consider there to be n galaxies in a volume V of space in the luminosity range L and L plus dl, or magnitude m and m plus dm. Then, the galaxy luminosity function is given by this expression. Integrating over this function over all the luminosities will give the total number of galaxies in the volume V. This analytic form of the luminosity function was first proposed by Paul Schechter in 1976 and is therefore known as the Schechter function. The Schechter function seems to represent the distribution of galaxies well given by this expression. There are three parameters of this analytic function. L star is the luminosity of galaxies near the break, also called the knee in the luminosity function. Phi star is the density of galaxies of luminosity L star, and alpha is the slope of the luminosity function at the faint end. It is almost a cosmic mystery as to how this complex problem is so well defined by such an elegant and simple mathematical function. Astronomers like the Schechter function because it's relatively simple, does a decent job of fitting the observations, and is easy to deal with analytically. However, there are dangers to using it. First, note that the density of galaxies appears to grow without bounds at the faint end, meaning the Schechter function predicts an infinite number of faint galaxies or an infinite amount of light. Neither of this is correct. One must also keep in mind that these fits and determination of the parameters are based on observations which have various sorts of bias. Very luminous galaxies, for example, are rare. We don't see any galaxies with absolute magnitude -24 near the local group. So, we must rely on samples covering huge volumes and large distances to count them. But at those large distances, we cannot detect at all the very common low luminosity galaxies which we can find in abundance in the local group. So, in order to make a plot like this, one must mix and match results from different surveys, each with its own set of biases. This is a complicated business. From the distribution, now let's move on to the relations between observed properties of galaxies. Back in the 1970s, astronomers found some quantitative relationships between some properties of galaxies. The interesting point here is that some of these relations are between quantities which are independent of distance, yet can tell us something about other features such as luminosity or mass which are dependent on distance. In fact, as we will see, they can be used to measure the distance to the galaxy independent of redshift and also predict the Hubble constant. Let's begin by noting the fact that the gas disk observed using the 21 cm radio emission extends much beyond the optical disk of spiral galaxies. In spiral galaxies, the disk of stars and gas is rotating around the center of mass as shown in this figure. This figure represents the h1 radial velocity field of the nearby spiral galaxy M33. The colors in the image correspond to Doppler redshift and blue shift of the gas relative to the center of mass. When such a disk galaxy is viewed edge-on or at least at high inclination, the 21 cm line of neutral hydrogen appears as a line with double horn profile. The center of the double horn 21 cm line gives the recessional velocity of the galaxy with respect to the observer. So, it is used to measure the distance to the galaxy. In case of nearby galaxies, Where the distance to the galaxy is known through other methods, it can predict the Hubble constant using the relation V is equal to h naught d, where the symbols have their usual meanings. On the other hand, the width of the line is equal to the rotational velocity of the galaxy. It is a common practice to use the 20% or 50% of the maximum flux to determine the width of the H1 line. The double peak of the H1 line arises because of the flat rotation curve of the disk. A rotation curve is a graphical representation of the rotational velocity v as a function of the distance r from the center of the galaxy. In fact, it is observed that rotation curves of many galaxies have nearly constant velocities as a function of radius. Essentially, the galactic rotation curve shows that the center of a galaxy rotates as a solid body while the outer part is flat. This is unexpected in a standard scenario, as is the case with the rotation curve of the solar system, because as the radius increases, the velocity should decline. But a flat rotation curve evidently shows there is more matter in the disk than observed in the stars and gas. In fact, the flat rotation curve implies that the total mass of a galaxy can be given by this relation, where r is the distance from the center of the galaxy corresponding to the flat part. The exact value of r is not important as long as velocity as a function of r remains constant. This means that the dynamical mass of a galaxy, when compared with the visible mass comprising stars and gas, reveals the presence of dark matter in spiral galaxies. By measuring the rotation velocity for a set of edge-on spiral galaxies, in 1977, Brent Tully and Richard Fisher found that the maximum rotation velocity of a spiral is related to their luminosity, such that more luminous galaxies rotate faster. This is known as the Tully-Fisher relation, where the slope alpha is found to be around 4. However, the slope as well as the scatter in the Tully-Fisher relation decreases for longer wavelengths. This is expected because the blue bands are affected by different amounts of star formation and dust absorption. Since luminosity is related to the maximum rotation velocity Vmax, by knowing Vmax and the apparent magnitude of a galaxy, one can predict the absolute magnitude and hence the distance to the galaxy. For a cluster of galaxies where tens of galaxies are observed, one can measure the distance to each galaxy via the Tully-Fisher relation and then take their average to calculate the distance to that cluster. The further away is the cluster of galaxies, more the Tully-Fisher relation is shifted downwards on this diagram. For instance, here Tully-Fisher relation of two galaxy clusters at different distances are shown. The one at the bottom is Abell 1367, which is at a distance of around 94 megaparsec, much farther away than the Fornax cluster shown at the top, which is located at a distance of around 13.5 megaparsec from us. Knowing the distance to any one of these clusters will lead to the estimation of distance to the other by measuring the relative difference delta d between the Tully-Fisher relation of the two clusters. Sandra Faber and Roger Jackson found a relation analogous to the Tully-Fisher relation for the elliptical galaxies. They discovered that the velocity dispersion in the center of elliptical galaxies scales with their luminosity. In other words, more luminous galaxies have higher velocity dispersion of stars and vice versa. But galaxies with high velocity dispersion are also known to have high mass to light ratio. That is, they are more massive than the sum total of their stars and gas, in turn meaning that they have a lot of dark matter. These correlations therefore imply that galaxies with high velocity dispersion are more dark matter dominated than their low velocity dispersion counterparts. In order to further reduce the dispersion in a relation for ellipticals, astronomers discovered what is now known as the fundamental plane. The reason for constituting such a relation lies in the fact that the scatter and the scaling relation reduces greatly when a combination of two rather than individual parameters are plotted against one another. As can be seen in the example here, the Faber-Jackson relation implies that the luminosity is proportional to the velocity dispersion of stars. But the velocity dispersion in turn is correlated with the size r of the galaxy, albeit with a large scatter. Also, the luminosity is correlated with the radius of the galaxy. Therefore, combining these information together, one can find a model which matches the observations better than the individual quantities. This is called the fundamental plane. The fundamental plane allows us to use any two of the three quantities to predict the third without measuring it. The fundamental plane has been represented in many different ways in the literature, but it essentially shows that some combination of luminosity, size, and velocity dispersion of stars in an elliptical galaxy is a constant. But what do these relations mean physically? The virial theorem tells us that the kinetic and potential energies of a body must be related such that the sum of twice the time averaged kinetic energy and time averaged potential energy is 0. Consider a spiral such that a small clump of gas with mass small m moves in a circular orbit of radius r around a big central mass capital M. Here, the gravitational potential energy and kinetic energy are given as usual by these expressions, which leads to the conclusion that the square of velocity is equal to gm over r. Now, if we further assume that the mass to light ratio for all spiral galaxies is a constant, even when the distribution of mass is more complicated than the Keplerian case, the velocity dispersion of stars will have a similar relation to the total mass and radius of the system. Therefore, leading to the fact that the square of velocity dispersion of stars is proportional to the ratio of luminosity to radius. Of course, we've oversimplified in this derivation because all elliptical galaxies do not have the same average surface brightness or central surface brightness. In fact, the giant luminous galaxies have a somewhat lower central surface brightness than the smaller ones. But among the giant ellipticals, it is not wrong to say that all of them have comparable average and central surface brightness. Another related scaling relation for elliptical galaxies is the dn sigma relation, where dn is the diameter of the ellipse within which the average surface brightness of the galaxy is 20.75 magnitude per square arc second in the B band. Here you see this relation for the ellipticals on the left and S0 galaxies on the right hand side. The dn sigma relation describes the properties of ellipticals better than the Faber-Jackson relation. Also note that the quantity dn is almost independent of surface brightness of the galaxy. To summarize, today we learnt about the different types of galaxies, their properties and scaling relations between them. I hope you learned something new today. Do let me know in the comments what other topics you would like me to cover on this channel. I'll see you next week. Until then, take care.